Let's start the seminar, and we have a guest, Lluís Hurtado Gil from Spain, and I give the floor to Ensar to present him. Yes, please.
Okay, I have known Lluís how many 2 years or 1 year, I even don't remember. Lluís is from Valencia. He's just working on the large-scale structure studies, and at the moment he's just trying to get the most out of those very good properties of the Alhambra Survey, and of course we are.
Yeah, we'll introduce the survey as well. Okay, so thank you, Anna, and then for the introduction. And thank you all of you for inviting me this month to Tartu. Really having a very nice time here. So, exactly, what I'm going to talk to you today is about the Alhambra Survey, which is a galaxy survey developed the last 10 years by a Spanish team. And then I will show you an example of the kind of works that we can do with the Alhambra Survey and its data. So this work is done together with Professor Vicente Martinez and researchers Pablo Arnalte and Alberto Fernandez from those. Now they are each one in a different institution. So now the Alhambra Survey. Alhambra stands for that funny long name: Advanced Large Homogeneous Area Medium Band Redshift Astronomical Survey, and it's a photometric redshift covering 4 square degrees of the sky, separated in 8 little windows, each one pointing in a different direction. You have here the positions of the 8, 7. Okay, only there are 8, but in this picture there are only the 7 that are already finished. Are those ones? So they are pointing in very different directions. So the morphology of the survey is 8 pencil beams, very deep, because Alhambra is a very deep survey, reaching redshifts up to 7. So you can imagine those 7 pencil beams in very different directions of the universe. In addition, as I told, it's a photometric redshift, a photometric survey, and we are using 23 narrow band filters in the optic and the 3 common filters in the infrared. So why this? The aim of doing this kind of photometric survey, deep photometric, and with 23 filters, is response to, well, you know, the main difference between a spectrographic survey and a photometric one is that with the photometric one you have the full image of your sky, and then you can calculate everything you want from every object that you have in your image. While with the spectrographic one, you need to cut that part of the sky and observe it through the spectrometer. So that always includes some problems of fiber collisions, and it is difficult to observe 2 sources that are very close to each other because of those problems. So with the Alhambra survey, we have our image, and every object detected in the image, we have the information about him. And in addition, as it is a very deep survey, we have very good images of our galaxies and clusters. We'll talk a little bit more about that later. So about the quality of the redshift, which is always the kind of one of the most important things you're trying to get when you're doing a survey. This is a comparison between spectrographic and photometric surveys for more than 7,000 galaxies, and as you can see, there is a strong agreement. So we are pretty sure of the quality of the reliability of our data, which is already public. You can download it here. more than 300,000, this is around 380,000 different sources, most of them galaxies, including quasars and also stars. Or just email me, because I know this is a little bit too long to memorize it, so just feel free to contact me and I will send you any information you want. Okay, so this is the overview of the Alhambra survey. If you want more information and I can give it to you, just ask me now or at the end of the talk, and we'll talk a little bit more about this. So the work we are doing, we took the whole Alhambra survey and selected the data we were interested in, which includes a galaxy satisfying flux in this. The band I didn't describe it. Sorry. Band I is the integration of this filter here, which corresponds to the filter centered in 814, which is used by the Hubble telescope, so it's like a reference. So we limited the galaxies with this flux here. We took a redshift between 0.35 and 1.25 because we were going to do is a study of large scalar structure and 2-point correlation functions, and therefore we need completeness in our samples. So we select this interval of redshift, which is where we have enough density of data to do those kind of calculations. We apply the star-galaxy separation. The Alhambra survey includes its own parameters to perform that kind of calculations. And the final catalog includes around 170,000 galaxies. And this is the overall density of the survey. So this is what I was telling you about the 7 pencil beams. This is more or less how the final sample looks, with our galaxy in the center, of course. And this is the sample we are using to the calculation. Those are the mathematics. I already told you about the 2-point correlation function, but indeed what we are doing is the projected correlation function, which, as you probably know, is the most common in the bibliography. This function was proposed by Davis and Peebles with the intention to correct the possible errors in the redshift estimations. So with the conventional 2-point correlation function, given a galaxy here and another one here, we are interested in calculating the probability of having those galaxies separated by the distance s. But with this projected one, what we do is, given the line of sight, which is this green arrow, we calculate the parallel component and the transverse component, and we use those two distances in our estimation of the 2-point correlation function. So we are interested in having two galaxies separated by those two distances and performing that particular scheme here in the picture. Okay. So once we apply, in this case, the Landis-Salai estimator for the correlation function, now we integrate, is this integral here, we integrate along the parallel component. Parallel component here is represented by pi, and the transverse one as r sub p. So here, when we integrate along pi, what we are doing is absorb this distance, and therefore any possible error in the redshift estimation is mostly found here and therefore absorbed by this integral. So in the end, what we have is that these two galaxies with this function are separated by this distance in a projected and transverse plane to our line of sight, and therefore the name of projected correlation function. For calculations, it's important to know that this limit here must be limited to, we used 2000 h-1 megaparsecs, because if you use a higher distance, you start including error and no more information. Because imagine just that this galaxy is not here but here at the top of the screen. So those galaxy 1 and 2 are so separated that there is no real correlation between them. So you're not interested in that kind of pairs. Therefore, the limit here. Okay, this is how the samples I describe later look on the magnitude redshift diagram. This is the work developed by Paulo Arnalte, and he separated the redshift in 4 intervals, overlapping intervals, which are described by the blue lines, then red, then green, red, and finally brown. And the color bands, a little bit horizontal, are cut in the magnitude, because as we have this selection function here, we want to compare the distributions, the projected correlation functions, for samples with the same magnitude or comparable magnitude. Therefore, those thresholds in the luminosity. So we are going to compare in 2 directions, redshift and luminosity. And those are the results. For the 4 redshift beams, what we found is that basically the higher the luminosity, the higher will be as well the amplitude of the curve. So more brighter galaxies perform bigger clusters. We could say more or less that it's bigger clusters. This is this formula here is the model used for fitting these curves. It's just the usual power law, and the meaning of those 2 parameters, R sub 0 and gamma, more or less can be understood as R0 as the size of the cluster. So R0 is the point where number 1 touches the curve. Okay? So the higher the amplitude of the curve is, this R0 will be bigger and the curve will touch it farther. While the gamma means the slope of the curve. So the bigger gamma is, the most vertical the curve will be, and therefore a cluster will be more clusterized. So this is the first conclusion we found from that luminosity segregation point of view. This is the summarize of the behavior of those 2 parameters, gamma and R sub 0. Gamma is more or less constant with luminosity, which means that it creates those parallel lines we can see here, while R sub 0 tends to be higher with the luminosity, as I was explaining you. Something curious is that along the redshift, we see that the farther the redshift is, the curves are present lower R sub 0s, except for this being around 0.7, which suddenly appear to be higher values of R sub 0 than the rest of the redshift beams. Why? We think, and we are pretty sure about that, this is because a strong early type galaxies structure that can be found in one of the Alhambra pencil beams, particularly that one which is pointing to the same area that was studied by the Cosmos Survey. If you are ever worked with Cosmos Survey, they found that enormous structure of red galaxies around precisely 0.7. So the appearance of that structure in that volume, we think, creates this break in the monotony of the results. Okay, But these studies are done for separations between the galaxies bigger than 0.1 h-1 megaparsecs. But as I was telling you, Alhambra is a photometric redshift, very deep. We have very good information of our clusters, and we can see the details inside the clusters. What I like to say is that Alhambra is not only a good telescope, in the sense that we can see very distant objects, but it's also a good microscope, because once we have a cluster, we can study even the faintest galaxies inside the cluster and have a very detailed image of the clusters, and also the galaxies that are closer to us can be studied very well, morphology, compounds, etc. So we did a comparison between Alhambra and 3 other photometric surveys, which are the Primus survey, DIP2, and the Sloan. I selected the data from those surveys following the constraints I already explained, so they're the same for the 4 surveys in order to compare them with the same conditions. And we calculated the nearest neighborhood function. This function is telling you which is the probability of finding your closer galaxy at a given distance. So the higher the probability is at very close distances, that will mean that you have clusters with very high density of objects, and therefore your closest galaxy is very close to you, because in your cluster you see every single neighbor around you, and therefore you find your closest one closer than other surveys. And this is what we see here. For Sloan, if you have a galaxy, the probability of finding a close neighbor is smaller than for the rest of the surveys. For Primus and DIP2, the result is more or less the same. But for Alhambra, we can see that here, that for very short distances, we already have closest neighbors of our galaxies. Even more, you can see the slope of this curve is more or less linear, but here you have something like a little bump. This bump, we didn't study it in detail, but I think this is a symptom of a structure already, of finding a structure of the clusters with this very simple function. Anyway, as we saw this, we decided that it would be interesting to study the previous function in those very short distances. And therefore, we selected only one of the previous samples, the one which is situating the magnitude threshold around minus 18.6, and separated again in 4 redshift beams. These times redshift beams are not overlapping, but this is just a personal decision. And the results, this is the 4 curves are those here, are the following. As now we only have one magnitude threshold, you are only seeing one curve, unless not 4 curves as before. So what you see here is that in the previous calculations, the curves were started here, okay, around 0.1, and those 4 beams were not included. And as you can see, those 4 beams are precisely the most interesting, because at very high redshift, the tendency, the slope of the curve is broken into two different curves. So we see that at those very short distances, the curve presents 2 different slopes. And when you move toward closer redshift, that slope is disappearing. You can see it all together here. You can see how at very short distances the curves are behaving more or less the same, so there is no clear evolution with redshift. But for distances bigger than 0.1, the curves appear again on parallel curves with different slopes. So they are somehow like starting like this, and with redshift they start to match into one single power law function. This result was already introduced by this paper here by Watson, Berlin, and Sender, which is called A Cosmic Coincidence, the Power Law Galaxy Correlation Function. Power law is assumed to be a good approximation of correlation functions for galaxy distributions, but what we see here is that once you include very short distances, there is no one single power law. You need another model, or at least two different power laws for the two regimes. So that introduces interesting results that should be understood from the point of view of galaxy evolutions and intramedium cluster physics, which we'd like to develop in the future, because these distances here are closer to the distances where gravity is not enough to explain relations between galaxies, and therefore you need some other physics. In order to study this result deeper, we performed another segregation, the spectral segregation, in which we separated the samples between early type and late type galaxies, which is something like talking about red galaxies and blue galaxies, or elliptical and spiral and irregular, or old and young galaxies. This is a magnitude color diagram where you can see how the two big areas corresponding to our segregated populations, because this segregation is done using again the data included in the Alhambra Survey. In Alhambra Survey, for the estimation of the redshift, we used the Bayesian photometric redshift, which includes several priors for the spectral energy distribution of the galaxies. So we use that information to separate between early and late type galaxies, and after that we performed this calculation, and we found that it was working pretty nice, and there was a clear separation between the two different kinds of galaxies. We can talk a little bit more about that later, because I didn't explain it properly. And this is how looks again the redshift magnitude diagram with our previous four bins for our blue and red galaxies. And then the results are those here. As you can see, for red galaxies, there is no clear appearance of that double behavior in the curves. So in this case, the one single power law approximation remains valid. But for the blue galaxies, the late type galaxies, you can see the breakpoint around 0.1, 0.2 in the four redshift bins, which tells us that this double behavior in the curves is therefore responsibility of the late type galaxies. We tried to look for an explanation of this behavior, but we found this conclusion here by Salyak in 2000. This deviation, he was talking about precisely this result, corresponds to late type galaxy clustering, probably down to the tendency to cluster in lower mass halos with a smaller virial radii. The result is already from 2000. As long as I've seen in the bibliography, this is the first work calculating the correlation function down to these short scales I was talking about. So this is a result more or less expected, as you can see, but at the same time implies that we need to understand better some other phenomena. This I already said that. For future work, we would like to find some new models different from the power laws to describe this behavior in the curves. We are thinking about the halo occupation distribution, which describes the one halo term and the two halo term of the galaxy contributions to the functions. And for the a little bit more distant future is another survey, the JPASS survey. JPASS is a new survey we're starting with Spanish-Brazilian collaboration that pretends to more or less repeat Alhambra, but in a much wider volume. We're talking about 8,000 square degrees of the sky, and not with 23 filters, but with 58 filters. So it's going to be like a big brother of Alhambra. And JPASS for sure will provide very interesting new data where we can repeat those calculations and find new conclusions and results. And that's all. Thank you very much for your attention.
Thank you. So please, questions? Yes.
Does the Alhambra data, the public data, includes also the posteriors for the photometric redshifts, or just single value and some arbitrary error?
It probably includes only the value, only in single value. But even if it's not ready to download from the web page, we can take it and ask for the people who has been doing this work and find those data and send it to you. So I think there will be no problem with that. Because you probably know about that when you do the Bayesian photometric redshift, your results you calculate the probability of having a galaxy in a given redshift and having a certain type of galaxy. So this information has some huge matrix, and for the thousands and thousands of galaxies that we have, it's a lot of information. But it is prepared, not to download, but we can access to this data and work it. Actually, people in the Alhambra collaboration insist on that, because this is the proper way to deal with this kind of data, going straight to the whole matrix and not only to a certain value.
Well, more questions?
Can you just explain more what Celiac said? Because you know that that this thing that if later galaxies get clustered in small halos, this explains the slope at the smallest distance. But then the slope gets flatter later on, and it's not so easy to explain why.
Yeah. This sentence here actually, I found firstly this sentence in a paper by Sehavi in 2001, where doing calculations for distances bigger than 0.1, they already found that the first beam was too high compared with the rest. So as it was only one beam, they said, okay, we don't have enough information, but in case of, we think that could be an explanation. So that was everything we found there. So why that break point in the later galaxies? This is a matter of cluster evolution probably, and I'm really not an expert on that field. So with the theoretical.
But now if you compare those especially those the correlation function or late type galaxies in different redshift pins, do you see any evolution?
If we compare,
Yeah, because it's difficult to say from this figure.
Evolutions.
If we look only at this
You mean
late type galaxies and then look to the correlation function as any evolution with redshift, it's very difficult to see from the.
No, I didn't plot it.
There is no really.
Yeah. I didn't plot it because basically you find the same that you can find here. So for very short distances, we cannot say that we have an evolution. We can only say it for the long distances. So it looks like we have two regimes for the clusters, some kind of hardcore clusters and then outskirts of the cluster that behave in a different way.
There are filaments that are growing into clusters. Spiral galaxies are mostly fit.
Would you say that filaments work in those ranges of distances? I don't know.
Yes.
Yes. Okay.
Scale is fine, but I don't know.
Could be this filament scale. This is filament.
I mean, this looks like the outskirts of the clusters are getting more and more populated. So obviously someone is feeding them. Could be interesting idea. Yeah.
The innermost points on the plot, they are already very bound galaxy systems, like almost merging galaxies, like a couple of tens of kiloparsecs are the first points in this plot.
You mean the galaxies here?
This pair is almost a united galaxy already.
Yeah. Actually, in the Alhambra Survey webpage, you will find some beautiful pictures taken from the survey. And some of them are precisely of galaxies interacting to each other, and you can see real physical interactions. There is one, this is my favorite one, where you can see how a galaxy is pulling an arm from a spiral galaxy, and the spiral galaxy has lost his shape because the other one is spreading the arm. So that kind of interactions, yes, actually are probably happening. The point is that this is already, this bin here is already the non-reliable bin, because you can see the amplitude falls down. This is because this is the limit of the Alhambra, this distance here. So this is not enough. Alhambra is not enough deep to see this detail. Some people say, although, that even with deeper surveys, the intracluster light, I mean the light that different galaxies are emitting inside the cluster, wouldn't let you to see into the necessary detail the interactions of the galaxies. So yeah.
Well, more questions? Well, if it is none, then thank you again.
Thank you.
And next Wednesday we don't have a seminar because all of the action which is planned for the next week.